All right, I believe we are live. So people should start joining pretty soon. And of course, you would just post your questions from any of the things, any of the resources. I imagine you might have questions from the practice test, the last test, the actual unit test, worksheet 6S. Those are the only three I can think of right now. I imagine you might have other questions, and if so, we can bring that stuff up and answer those questions. I tried to jot down some notes, some things that I think that you need to focus on for the test. So what we'll do is I will just keep track of that. I'll check them off as we go through them. And if there aren't any questions, I will go through that list. And as you guys have questions, I'm sure it will be on that list. I'll check those things off. But we should be able to get through it all. And I think you'll do fine. Okay, so I know people will start joining. There's no questions at the moment, so I thought I would go ahead and start on something. So the first thing I'm going to start with is, let's just start with the combined gas law. And there's a couple different ways that a couple different things. Let's see how thick is there it is. There we go. So combined gas law. And there's different ways that this can be approached. One way that it can be approached is by just straight up calculations, right? So we have our P1, V1, T2 is equal to P2, V2, T1. And so the question would give you two sets. And this is how you know, a lot of people ask, a lot of students ask, how do I know when to use each one? And what you have to look for is some keys. Combined gas law, one of the things that you really need to look for, I'm gonna put this in pink, is two sets of data. And what I mean by that is two pressures. Maybe you have also, and usually you're going to have a couple different things, two pressures, two temperatures, two volumes. And so, and it's a change. So, and that's one of the things when it says after or before or something along the lines of there's a change in tense of the way that of the question speaking. And hopefully you can read that. Change in conditions. Okay, and that's when you know you're going to be using the combined gas law. So let's look at an example in your. Let's go to the test. Let's see, so, all right, so from the actual test, if we're looking at, okay, look at number 4 right here. And it says a sample of 0.010 moles of oxygen gas is confined at 127 degrees Celsius and 0.80 atmospheres. What would be the pressure of the sample at 27 degrees in the same volume? Okay, so now we have a change in temperature. There are two temperatures here. A change in temperature, you know, the conditions are changed. It says the same volume. Well, it never gave us a volume, so we can just say whatever, and we don't have to include that. And what would be the pressure? So the new pressure. There's an old pressure, and then there's a new pressure. We're looking for the new pressure, so that's the P2. So that's one way in which the combined gas law can be used. You have to look for that change when you have a change in conditions. I refer to it as dynamic. The difference between dynamic and static. Static means it stays the same. Dynamic means it changes. So number 4, it's changing the conditions. So you're going to have to plug those numbers into the combined gas law and solve for the new pressure. So that's one thing you're going to need to pay attention to for, and these are things that you need to know in general, but also for the retake. So, okay. So I'm going to go back to the bamboo paper. And those of you that have just joined, please submit questions. While I'm waiting for you guys to ask specific questions, I have a list of things that I want to go through that I think will be helpful. And so I'm going to go through that list, and we can jump around and come back to it or whatever. So right now I'm in the combined gas law. Okay. So that's one way in which the combined gas law can be used. Another way is the same sort of equation, same sort of thing, but now it's going to ask for, it's going to ask a question in sentence. So we'll put this one, this is calculations. This is a calculations. Actually, you know what, since we're doing calculations, I should mention that you guys may have seen some questions. There might be some drawings. Let's see. Let's see, like bulb 1, bulb 2, bulb 3, and then it's like a tube, and it all goes into, there's a stopcock here, and you know, there's maybe one for each one of those, and the tube goes into a much larger container, okay? And it wants to know if it has, in each of these containers, has a gas in each of these containers, and releases them all into this big one, what will the new whatever it will be, okay? And so in a condition like that, it's usually saying, so there is, you know, 2 liters at 0.2 atmospheres. And then there's 4 liters at 0.3 atmospheres. And then there's 6 liters at 0.4 atmospheres, hypothetically. And they're putting it all into a 15-liter tank. What's going to be the new pressure? And so what you're going to have to do is you're going to have to go through and do combined gas law for each one of these, okay? So, you know, if you have 2 liters at 0.2 atmospheres, and it's going to 15 liters, and it's the same temperature, so you would, oops, sorry. So you're going to use this P1V1 equals P2V2. And so you're looking for P, so you're solving for P2 for each one of those. And so it's a little combination with Dalton's law, actually. So you're going to have P2 is equal to P1 V1 over V2. And you solve for each one. And let's say it's gas A, this is gas B, and that's gas C. And when you get the P2 for each of them, you would say the P2 of A plus the P2 of B plus the P2 of C is equal to the P total. And so that'll give you the new pressure there. So that's a combined gas when you're taking from each one. You know what? You guys aren't even seeing this. What happened? Oh my goodness, what happened on my stuff? I feel like all my question answer went away too. Okay, let's see. Oh, there we go. Okay, so I was doing all that work and you guys weren't seeing it. My apologies. So you have this, each of these 3 containers. This is just as an example: 2 liters at 0.2 atmospheres, 4 liters at 0.3 atmospheres, and 6 liters at 0.4 atmospheres. And all 3 of them are going to be released into a 15-liter tank. So you're going to have to use the combined gas law. It's a constant temperature. So you use the P1V1 equals P2V2. And you're solving for P2 because that's what you don't have here. And so you have P1 V1 over V2. And you plug those in and you find the P2 for A when it goes in, the P2 for B when it goes in, and the P2 for C when it goes in. And then you add them all up. So there's a Dalton's law aspect to that. And you get the P total. And that'll give you the P total that goes into here. Okay, so that's another way that the combined gas law can be asked. So that's a little tricky. Right before I started that, I feel like there was a question. Oh, there's a few questions. Oh, I just didn't have it linked up. Okay, so let's go ahead and start. Emma had a first question. Can you please review the free response? I wasn't there for the lab, but in a session with the group before the test, I got caught up and thought I understood the lab and practice test example, but I can't seem to get the one on the test. Okay, so let's take a look at, I'm gonna go ahead and share the test free response. The test free, the gases unit test, there we go. All right, so is this the test? Guess, oh, that's the practice test. That's not the one I want. I'm so sorry. There it is. Okay. So the whole free response is all together. So you're looking for the whole free response. Okay, that's fine. I can do that. So you are collecting O2 gas over water. And whenever you're doing it over water, you're using Dalton's law. So the free response is going to be exactly the same on the retake test, meaning that you're going to have to go through a lot of the same steps. Very similar to the lab. This one was that we're collecting a different gas, but you are having the partial pressure of oxygen gas equals the partial pressure of whatever the atmosphere is, whatever the barometric pressure is. And this was the PATM right here was the atmospheric pressure in the lab, okay? And then the partial pressure of the water, that is right here. It tells you, it'll give it to you in the problem, or it'll give you a table that you need to reference it in. So the equilibrium vapor pressure of water at 23.4 degrees Celsius is 21.6 degrees torr. So it was P total, because this is really, and maybe I'll write that underneath it so you guys can see it. P total. Okay, P atmosphere and P total are the same thing, okay? So P total equals P of water plus P of oxygen gas. So P total minus P of water equals P of oxygen gas, a little algebra, okay? And so you get the 762.6 minus the 21.6 gives you the pressure of the oxygen, which is 74.1 or 741.0 torr. All right, that should be pretty straightforward, pretty easy. Calculate the number of moles of oxygen produced. Well, once you have the pressure and you have all the rest of the conditions, which is the volume, right? You had 182.4 milliliters. You have the R, which is the gas constant, 0.0821 liters atmosphere over mole Kelvin. And then the temperature, which is the 23.4, because you see how it's the 23.4 degrees Celsius, that's the air temperature and the water temperature. So you add that to 273 because you have to do that in Kelvin. And the 741 torr has to be converted to atmosphere, so you have to divide it by 760. So once you have your pressure in atmosphere, you have this in liter, because it gives it to you in milliliters. You have the universal gas constant, and you have your temperature in Kelvin. You solve for N, the moles, and you get the 0.00731 moles of oxygen. Hopefully so far you're sticking with this. This is pretty straightforward stuff. Once you have the moles, then you can convert it to grams. Well, for the balanced equation, we give you the balanced equation up here. Okay, so for every 1 mole of oxygen, it gives you 2 moles of hydrogen peroxide. So you get the moles of oxygen gas from number 2. You're running it through your bridge. For every 1 mole of oxygen, you have 2 moles of hydrogen peroxide. For every 1 mole of hydrogen peroxide, that's 34.0 grams. So you're converting it to grams, and you get the 0.497 grams of H2O2, or hydrogen peroxide. Okay. Now, once we have the grams, it says to calculate the percent of H2O2 by mass in its original 6.951 grams aqueous sample. Now, for this one, since you have the grams here, remember that hydrogen peroxide is a solution. There is some solid hydrogen peroxide inside a water solution of, so there's a lot of water in there too. So there's water and solid hydrogen peroxide. It's dissolved, so we're trying to find the percent of it in the total. So that's 0.497 divided by 6.951 times 100. That's 7.15%. So hopefully that makes some sense. I would say that this first page, most students did pretty well with. You know, they got going pretty, I think it makes sense. Number 5, that starts where it gets a little sketchy. There is a really easy way to do this. Really easy. Mole fraction is basically the same as partial pressure. And so before I go through all this, why don't I go back to my bamboo paper for a moment. Okay. And I'm going to go to the next page. And so I suppose this is 5A and B. This is free response, okay? So they want to know the mole fraction of water vapor and oxygen gas. Both of these are a gas. Okay. Now, this is the hard part to remember. Mole fraction, which is the moles of your gas over the total moles, is equal to, right, that's mole fraction. We'll just call it, that's mole fraction right there. The mole fraction of your gas, which is also equal to the partial pressure of your gas over the total pressure of your gas. So that means that the moles of gas over the total moles is directly equal to the partial pressure of the gas over the total pressure. Those fractions are equal. They're not the same numbers, but the fractions are equal. So the super easy way of doing that was saying, oh, the partial pressure of, let's say, water vapor over the total pressure will be equal to the mole fraction of H2O. And this is the answer we're looking for. So all we had to do was put 21.6, and the units don't matter for this, 21.6 torr over 762.2 torr. And that was equal to 0.0283, and that was the mole fraction. So there's no units for it of H2O. That's all you had to do right there. We gave you the numbers. This number came straight out of the problem, and this number came out of A. So there's a shortcut here. All right, now, if you remember, these questions come off of past AP Chem exams, which means that this test was originally written, it was given on the exam, and I'll be willing to bet they had not intended for this to be the shortcut way to get to it. They intended for you to have to use the combined gas law, right? PV equals nRT, and solve for N of the H2O, which is equal to PV over RT. So you'd have to plug in all of your things and solve for that, and then put it over the total number of moles, which is the N total would be the N of that you had already solved for of the O2 plus what you just solved for now with the H2O. And then you would put one over the other and you would get your answer. So that's a pretty complex, involved way of doing it. They probably didn't mean for it to be this easy, and it turned out to be this easy, and how awesome is that little shortcut? So on the retake, that's all you have to really do. Don't bother going through the long way, just do the easy way for right now. And I was glad to see that people had noticed that. Some people did it the long way, which is fine, because that's actually the way that I solved it the first time too. So there's that. So let me go back to the test now. Okay. Okay. So, and then you solve for the oxygen gas, and you can do the same thing. Now that you've got the moles, you can just use the moles, or you just use the pressure like you had solved for earlier, and voila, you're finished. So that is 5A and 5B. And so I think that makes some sense. Again, super easy if you really look at it that way. And on the retake, do it the super easy way. All right, number 6. I will provide you with the root mean square speed equation, which is that right there. But it wants to know the ratio. We're not looking for the actual speed. I mean, yes, you're looking for the speeds, but you're looking for the ratio. You didn't even have to solve for the speed. I can't tell you the number of people that just straight up did the solving for the speeds and then just put the speeds next to each other, one right over the other. And I get it. That's one way to do it. But there, of course, is an easier way. And a ratio is the same thing as a fraction. And so if you have the root mean square speed of water over the root mean square speed of oxygen, you put one over the other. 3RT cancels out for both of them. So you're left with the molar mass 1 over the molar mass of water and divided by 1 over the molar mass of oxygen. So this probably looks a little confusing, but think about it like this. If it's 1 over a number, and that means that this number, the molar mass of water, is actually in the denominator because it's right here, 1 over that number. And in the denominator, when you get a fraction in the denominator, if you guys remember, you just flip it over. And that's why the molar mass of oxygen ends up on the top here. So you get the square root of the molar mass of oxygen divided by the square root of the molar mass of water, and you get your answer, 1.33. Okay? So, but of course, it doesn't really end there. On the test, I may have you do the ratio, or I may have you actually solve for it. And so you need to know both ways. And so I would tell you that, let me go to the bamboo paper. Okay, so, oops, oh, there we go, sorry. So number 6 on the free response would be URMS is equal to the square root of 3RT over MM. Okay, and the key things about root mean square speed, the R is equal to 8.31. Oh, I'm already forgetting. Joules. Is it joules per mole Kelvin? Joules per mole Kelvin. You can't really read that, can you? Let me try that again. 8.31 joules over mole Kelvin. Okay. And that's R. The temperature, of course, is in Kelvin. And molar mass is equal to, it's whatever the number is, it's kilograms per mole. Kilograms per mole. Okay? So you have to take your number, so the molar mass divided by 1,000. Right? Because the molar mass is in grams per mole normally. So you divide it by 1,000. So it's whatever your molar mass is times 10 to the negative 3, basically. So let's say it was the oxygen. It would be 32 times 10 to the negative 3 kilograms per mole. Okay? 0.032. All right, so now there's another thing here. Let me write down all of the units and see how you do with that. So we have R, which is, the units are joules over mole Kelvin, okay? Times temperature, which is Kelvin, divided by molar mass, which is kilograms per mole. Okay, so the kelvins cancel out, the moles cancel out, leaving you with joules over kilograms. Okay, and so it's root mean square speed. Speed. How is speed measured in joules per kilogram? Well, here's the fun thing. Joules is actually equal to kilograms times meters squared over seconds squared. So this is equal to, and remember this is still square root, it's square root of kilograms times meters squared over seconds squared divided by kilograms. So the kilograms cancel out. So then you're left with the square root of meters squared over seconds squared. And when you take the square root of that, it's equal to meters per second. So root mean square speed, the units are meters per second. Yes, I know, long and convoluted, but important all the same. So much fun. All right, so let's continue with the free response. All right, test, share. Okay, so now we're going to 7. When measuring the pressure inside the cylinder, what happens if the water inside and outside are not at the same level? More specifically, what happens when the water level is higher inside the cylinder? Okay, so basically, you know, I'm going to draw this too. A picture doesn't hurt. I say that. My drawings are so bad, they just might hurt. We're going to give it a shot anyhow. Okay, so 7 and 8, this is we're going to say free response 7 and 8. So these are the lab error questions. Okay, so for number 7, if we have a container, let's say here, and in this container we have water. Okay, and then we have the cylinder that's upside down. Okay, and then the water inside the cylinder is up here. Okay, which is higher than the surrounding water. So what's happening is that it's not the same level. So that means that gravity is actually pulling on this. Gravity is pulling down on this water right here. And since it's pulling on that water, it's pulling on this area up here, the gas up here, which makes it actually want to shift down and makes it look like a larger volume. Okay? So if you don't have them at the same level, it's going to pull it down and make it look like it's a larger volume than it actually is. And a larger volume equals less pressure. Now, some of you were astute about this and noticed that, so that is Boyle's law. That is part of the combined gas law. P1 V1 equals P2 V2. So this is what it's supposed to be right here. This is the real, or that's what it's supposed to be. I don't know what else to say. I'm just saying it's supposed to be this. Or this is supposed to be that. Yeah, we'll just say it's supposed to be. I'm lacking the appropriate vocabulary at the moment. Okay. Then what happens is on this side, this is what it actually is because the gravity is pulling down. What you end up getting. Okay, this is the error is on this side. Okay, so if you have your volume increases, then your pressure has to decrease. They are inversely proportional. Inversely proportional. So hopefully that makes some sense. Okay. All right. Then number 8, I might as well just do it right now, and you guys will remember what I'm talking about. Number 8, when I say, I mean, the question, what I'm saying is you'll remember the question, or you'll have it in front of you. It's saying, okay, so when it got inverted into the water bath, bubbles leaked in. Bubbles leaked in, okay? And when they did that, what's the effect on volume? Well, it's really just straightforward. More gas from bubbles, more gas from bubbles equals larger volume. That is what happens. Larger volume measured is what I should say. Larger volume measured. That was the effect. Very straightforward. Bubbles got in, then the bubbles, so that it was more gas, so it made it larger than it was supposed to be. Okay. Now, this was not so much of a problem. I think a lot of people got that. Well, I guess if you put bubbles in there, it's going to be bigger, more gas, larger gas. What got everybody was the B. A B. So would the calculated molar volume of hydrogen be too low as a result of this error? Explain. Okay. And so would it be too low? The answer is actually no. You don't get any points for that. You have to explain. Explain. We've got to get that down. We've got to practice that. Okay. So why is that the same? So remember that molar volume is equal to 22.4 liters per mole, okay? And so the mole came from the magnesium, right? It reacted with the hydrochloric acid to produce the hydrogen gas. So the magnesium, I should make that bigger. It looks like milligrams is what it looks like. Milligrams, or magnesium, sorry. So you measured it on a scale, and then you converted grams to moles. Okay, so that number on the bottom, that's constant. It doesn't change. It's always whatever you calculated from the original mass. That was not where the error is. The error is in the volume, okay? So whatever you calculated the molar volume to be, right? It's not, you didn't, maybe you got 22.4 liters, but probably not. So, what was the effect? What happened because of that? If you ended up with a larger measured volume, okay? So you got an original volume and it was calculated and you did it in milliliters, all right? So then what you had to do is you then had to convert it to liters, and you had to correct it to STP. So that means you had to use the combined gas law. P1 V1 T2 equals P2 V2 T1, okay? So whatever your pressure and your volume, which was in milliliters, but you had to convert it to liters, you then had to go to STP, standard temperature and pressure. So remember this, you're going for the new volume right here. Okay, so pressure 2 is equal to 1 atmosphere, or you can, it doesn't really matter, you can leave it in millimeters of mercury on too. The new temperature, T2, is standard temperature pressure, so it's 0 degrees, which is 273 Kelvin. Okay, this was your original, whatever your original temp was. Okay, anyways, you're going to solve for that, and that's going to give you just whatever the V2 is. So when you do that calculation, it makes it bigger, which is they're on opposite sides of the equation, right? So V1, why don't I do this? They're directly proportional. V1 to V2, directly proportional. So what if your measured volume is larger? If measured is larger, then your corrected volume is larger. And that corrected number is what goes on top. Corrected volume over the number of moles. And if you increase the size of the numerator, it increases the size of the number. Increase numerator, increase the size of the number. So hopefully that makes sense. I did it a little bit more detailed than I would expect of you. I'm going to go ahead and go back to the actual test so you can see what I had written on my key. So I said, no, it would be higher because the calculated volume would end up being smaller than it should have been with the same number of, larger, sorry, never mind. Larger than it should have been with the same number of hypothetical moles. Sorry, I was doing something else. Okay, it would be higher because the calculated volume ended up being larger than it should have been with the same number of hypothetical moles. The molar volume is liters over moles, the volume over moles. So larger volume would lead to a larger calculated molar volume. So that's what would happen. So hopefully, Emma, we just spent about 30 minutes on the free response, which is fine. That was half the test. Hopefully that covers that well enough and explains that. Of course, you can come and see me tomorrow anytime. Or I have you guys in class. What am I saying? I see you guys tomorrow, and then the test is on Friday. So you can ask me in class tomorrow. All right. Now we're on to the next question. We have 10 and 6 on the multiple choice. So I'm going to go ahead and scroll up. Number 10. Here we go. The system shown at right is at equilibrium at 20 degrees Celsius. At this temperature, the vapor pressure of water is 28 millimeters of mercury. The partial pressure of O2 in the system is. Well, this one is unfairly simple. So they're saying that that right here, the vapor pressure is 28 millimeters of mercury. And this is right here, this tall column right here is millimeters. This is mercury. This is millimeters right here. Okay. So the total pressure inside of that bulb that's pushing down is a height of 161 millimeters. So that's the total pressure. That means that 161 is combined of oxygen and water vapor. So what you had to do is take 28 from 161. 161 minus 28 is 133. That's what you had to do for number 10. So hopefully that picture won't be too bad. I'm trying to think of, do I have a picture like that on the test? I do not have a picture exactly like that, but I'm sure you will have to do a question where you have to find, this is Dalton's law, you're gonna have to find the partial pressure in the test. So that was number 10. So hopefully that makes sense for number 10. Just subtracting. Remember, you're just subtracting numbers. Anytime you're collecting it, when there's vapor pressure, when you see vapor pressure, you know you're going to be dealing with Dalton's law, right? Gives it at this temperature, at 20 degrees Celsius, this is the vapor pressure of water. That's a total Dalton's law pressure problem. All right, 6. Ooh, 6 is a fun one. 1.4 moles of potassium reacts with excess water at standard temperature and pressure, as shown in the equation above. The volume of hydrogen gas produced is, okay, it's a stoichiometry, and you will have to do stoichiometry with molar volume on the test. So let's walk through it. Let's put this in a different color. All right, multiple choice. Number 6. All right. So So we are given this equation that's already balanced for us, 2K plus 2H2O. Oops. Sorry, I'm trying to get the test so I can see it. Yields 2K plus, that should have been a superscript, sorry, plus 2OH minus plus H2. All right, and we're given 0.400 moles of potassium, and we're looking for the volume of hydrogen gas. So really, we're going from K to H2. So if we have 0.400 moles of K, for every 2 moles of K, we have 1 mole of H2. And according to the problem, it's standard temperature and pressure. And if we know that, STP, 1 mole equals 22.4 liters. So every time you see standard temperature and pressure, be thinking, oh, could I use standard temperature and pressure here? So 1 mole of H2 is 22.4 liters of H2. So you could do it like this, I suppose. This 2 goes away, and this becomes 0.200 moles of K, and 0.200. Well, the moles of K cancel with moles of K. Moles of H2 cancel with moles of H2, leaving you with liters of H2. So 0.200 times 22.4. So 22.4 times 2 equals 44.8. But you have 2 decimals there when you get done. So it's going to be 4.48. Well, I'm really just looking at it. The only option is C. Right? You don't. I mean, you're kind of guessing. I'm not guessing, but you're doing the best you can. If I do this, 22.4, I'll just trade, and then 4, and then take the decimal. There's 2 decimals. You guys remember that trick? There's 2 decimals here, so you can move the decimal place two places. 4.48 liters of H2, and that's C. So that was number 6. Definitely have stoichiometry using, there'll be definitely stoichiometry using the molar volume. So you had better be prepared for that. Okay. It looks like there aren't any questions in the queue. So I'm going to go ahead and go back to the list. All right. So let's see, where were we? Oh, we were with the combined gas law. We did a lot of it already. And I would say that the other part of combined gas law, besides the calculation, is sentences. And it's just wording, right? Remember that it's P1, V1. And this is what I would say. It would be easier when it's sentences, just remember like this, P1, V1, T1 over T1 equals P2, V2 over T2. And so if it says something about a sealed container, so that means the pressure is not going to change. Constant, oh, no, I'm sorry. Constant volume. If it's a sealed container, rigid sealed container. Keywords, rigid sealed container, that's a constant volume. So it means volume goes away, it's just P1 over T1, it goes P2 over T2. And if you increase temperature, what happens to pressure? Okay. And if it's a fraction like that, one over the other, they are directly proportional, which means you increase temperature, you increase pressure. So increased pressure. So you need to be familiar with the sentences and being able to kind of write out or walk through, talk through how changes in pressure, volume, or temperature lead to changes in the other variables. Okay, I see we have a question for multiple choice number 3 from Mikey. So let's look at the test number 3. All right. A sample of 9 grams of aluminum metal is added to an excess of hydrochloric acid. The volume of hydrogen gas produced at standard temperature and pressure is B. We have in front of us a stoichiometry involving molar volume. Okay, so I'm going to go ahead and share that Bamboo document with you again and walk this through. Okay, so this is multiple choice number 3. Aluminum metal is added to hydrochloric acid, and hydrogen gas is produced. Well, you have to produce something else because what happens to the aluminum and chlorine? So the aluminum and chlorine combine and form something, right? So aluminum is a metal, it's a 3+. Chlorine is a 1-. When you do swap and drop, you end up with AlCl3. When I balance this equation, my aluminiums are fine, the chlorine, I could add 3 right here, but I have 2 right there, so those aren't balanced. 2 can't go into 3, so I'm gonna have to erase that 3. The number they both go into would happen to be 6, so that's 6 HCl and 3 H2. So I have 1Al, 1Al, 6H, 6H, 6Cl. Oops, that's not gonna work. I'm gonna have to put a 2 over here, so now I have 6Cl, and that means I'm gonna have to put a 2 over there to make, okay, 2Al, 2Al, 6H, 6H, 6Cl, 2 and 3 is 6Cl. Okay, so now I have a balanced equation, and I start with 9.00 grams of aluminum, and I'm going all the way to the volume of hydrogen gas at STP. All right, so 9 grams of aluminum, I'm gonna have to, this is gonna be the full big thing. So 27, and you can round it now because it's multiple choice. You're not going to get a lot of decimals. So 27 grams of aluminum in 1 mole of aluminum. We're going to hydrogen. So for every 2 moles of aluminum, you have 3 moles of H2. And for every 1 mole of H2, if you remember, we talked about this in the other problem, 1 mole is equal to 22.4 liters at STP, and this is at STP. So we put 22.4 liters on top. And now we have to solve this. Easy enough. 9 goes into 27 3 times. This is 1. This becomes 3. These 3 cancels out. This is a 2. 2 goes into 22.4, 11.2 times. 11.2. So we have grams of aluminum cancels with grams of aluminum. Moles of aluminum cancels with moles of aluminum. Moles of hydrogen cancel with moles of hydrogen, leaving us with liters of hydrogen. And our answer should be 11.2 liters of H2, which, as it turns out, is letter B. Stoichiometry, going through the moles. It's all about the moles, my friend. Okay, so hopefully that answers your question. As I said before, there will definitely be stoichiometry involving moles and the molar volume, that 22.4 liters. Okay, so back to our questions, or not our questions, but our list of items that I think that you should review to get ready. And I'll wait. If you guys have if you come up with a question, please put it in there and I will address it. All right, so we've covered all of the combined gas law, ideal gas law. No, I didn't abbreviate that correctly. Ideal gas law. So this is where PV equals nRT. So the simple things, or let's just say this. Remember the postulates of the ideal gas law. So I wouldn't say that you necessarily had to have them all perfectly memorized, but you need to be able to kind of recall them. You need to be able to think about what they might be. And so using this kinetic molecular theory, that KMT we were talking about before, there's some things that you can just think about. So the first one, let's say, is that, oh gosh, here's the problem. I don't remember, I don't want to do them out of order, but it doesn't really matter. There is, they don't occupy space. Or you could say, if you guys remember Shariar, I mentioned one of his favorite words, volume is negligible. Okay, so that means we don't consider the volume of the molecule. The volume of molecule is negligible. That's the first thing I would say. The second thing I would say is that that it is that all collisions I'm spelling this wrong, I'm sure. All collisions are elastic, meaning no loss of kinetic energy. Okay. The third one I would say is there is no attraction or repulsion between molecules. Okay. Then I would say, never quite what I want. I'm trying to remember. I'm kind of, I have to be honest with you, I'm kind of struggling here. Oh, rapid random motion. Rapid random motion. Constant and it's constant. And so, and they move in a, and move in straight lines. Okay. And the fifth one we're going to talk about is that the temperature affects the speed or velocity. It's that kinetic energy. Okay. So, I'm sure they're in a different order on your notes, but that's kind of what they are. So the question would be, which ones happen normally? They happen all the time anyhow. So which ones happen for real gases too? Real gases. So we could say that so the number 5. So temperature affects the temperature, affects the velocity, if I'm getting that right. They are having rapid random motion. And we're going to say, I mean, it's not exactly true, but that collisions are nearly elastic. Collisions are nearly elastic, okay? Now, not so important. What's really important is which ones are not real gases. I mean, these are not, these KMT postulates don't happen for real gases. That would be the attraction repulsion. So there is attraction and repulsion. And molecules do occupy space. I mean, you could say that collisions aren't really elastic, but for the most part, the temperature makes it so that that's what happens. They don't lose a lot of energy. Okay. Now, which real gases are closest to ideal? And so that would be our monatomic, which are basically our noble gases. And our small diatomic. Because the small diatomic ones are nonpolar. So we're talking about the ones that have the least amount of attraction or repulsion. So, which then begs the question, what would deviate? What deviates from ideal? And so that's really, you're looking for polar molecules, okay? So it's kind of good that we're in the molecular geometry unit right now, because it would give you an opportunity to kind of go back through, okay, you should be able to figure out the Lewis dot structure for some of these and be able to identify, you know, if a molecule is polar or non-polar. Also, the large diatomic. So sometimes, because the atomic radius is large atomic radius, remember, it makes it kind of sticky, and induced dipole, large atomic radius. So, and this causes induced dipole, which gives you some polarity, causes induced dipole. All right, so those are the things you need to look for when you're asked about them. All right. Oops. Things that you need to pay attention to, again, with the ideal gas law, PV equals nRT. You can use molar mass in there. Remember, molar mass is equal to grams over moles, and N is equal to moles, right? So if molar mass is equal to grams over N, that means that N is equal to grams over molar mass, which means that PV is equal to grams over molar mass times RT. And if you're isolating for molar mass is equal to GRT over PV. You need to be able to solve for this. That's important. Okay. You could also have, when you're dealing with density equals mass over volume, which is equal to grams over volume. Okay. So if you have PV equals nRT, okay, now it's going to feel a little bit more complicated. Remember, when we're talking about molar mass, and we have molar mass is equal to grams over volume. Grams over moles. So PV is equal to G over mole RT. So if you want to just get density, I mean, or if you, however you want to plug it in, you can have moles being equal to G over V, that's the density, and then you have RT over P. So let's say you're solving for moles. Oh no, grams over molar mass, sorry. Again, you're solving for molar mass. This is just another way to solve for molar mass. My apologies for, so molar mass is equal to the density, G over V, RT over P. And usually when it does this, grams over volume, it's usually like, oh, it's 4.15 grams per liter. So it's always like 1 liter. So which makes it kind of easy to use, but that's how you can plug that in. Okay. Now that we've done that, let's do, I need to pick it up a little bit. We've covered a lot of it actually. This should be easy. Graham's law. We haven't talked about Graham's law. And remember that it's the rate of 1 over the rate of 2 is equal to the square root of the molar mass of 2 over the square root of the molar mass of 1, okay? So that means that 2, whatever the gas 2 is, it's a heavier gas and it's slower. And whatever gas 1 is, it's lighter and it's faster, okay? So you can see that they're kind of flipped around there. All right, so now this is important. Rate, you can see sometimes is in meters per second. Meters per second, okay? So you could have meters per second over meters per second, which is fine. You can also have the molar mass be density. It's actually, they're interchangeable for these purposes. So rate of 1 over rate of 2 is equal to the square root of the density of 2 over the square root of the density of 1. They do some funny things, but you can use that. Sometimes they'll say it's 1.63 times faster. So if they say it's 1.63 times faster, that means it's 1.63 over 1 is equal to the square root of the molar mass of 2 divided by the square root of the molar mass of 1. Okay? If they say that it's 1.63 times slower, 1.63 times slower, then it's 1 over 1.63 is equal to the square root of the molar mass of 2 over the square root of the molar mass of 1. Okay, so you know that's some things, some tricks that will be happening. Let me see if I wrote anything else down. I mean, I think I covered. Pretty sure I covered everything else. Let me just take a quick glance at the test to see if there's anything that I missed that I wanted to talk to you about. Oh, there is one other thing. That if you get the moles of a gas, that you can be able to convert it to molecules. Oh, I got your message, Aria. Okay, I'll see you guys. Oh yeah, so if anybody wants to come in early tomorrow morning, you know I get there early. I get there like 6:30. Oh, is tomorrow? Oh, not tomorrow. I get there like, so the test is not tomorrow. It's Friday at 6:30. So, but Thursday at 6:30. If you come in, don't come in at 6:30. Come in early in the morning. Come before class if you have other questions. So I can definitely help you guys then. All right, I'm sorry. So let's go back to that thing. So moles to molecules. I'm sure that you all remember that, or you darn well better remember, but just for the sake of whatever, let's say that it's 2 moles of the gas, right? It's a one-step bridge for every 1 mole, 6.02 times 10 to the 23rd molecules. So you're gonna multiply those together and you get 1.204 times 10 to the 24th molecules of your gas. Okay, so between the questions and the multiple choice and covering all the free response, I covered all the things that I believe are important for the test. So hopefully this time is helpful for you to be able to review. I don't know. So come and ask me questions or ask me questions during class tomorrow. But hopefully, again, this was helpful. So otherwise, I don't see any questions up there. I was going to end it here. Are there any last questions you guys want to type in there? I don't see any questions. So again, the test is Friday, 6:30 in the morning. If you need to take it later, you need to make sure you talk to me tomorrow. Don't come in the day of the test after we've already given it and say, oh, hey, by the way, can I take it later? Have a good night. Please get some sleep. Sleep is very important. Everybody's been really tired this week. I have been really tired this week, so I'm going to try to go to bed early too. All right, I'll see you all tomorrow. Thanks. Bye.